everyone. My name is Stephen Weigel, and today we're going to talk about treating scalar class sets like sets and seeing what all the equal tuning possibilities are for each scalar class set. Most of this is a little simpler than the previous videos because most of the substance involves adding, subtracting, multiplying, and dividing in slightly smaller doses. So let's go back to our major scale, which as a scalar class set is 5L 2S. Now that we have this information, we can say, which equal tunings can create a major scale, or form 5L2S, since 5L2S isn't always a major scale? By plugging in all of the possibilities of integers for L and S, we can get all of the scales and sort of draw them in a triangle. Now, much like the microtonal community at this point, I'm going to stick with scales that have two step sizes, so just L and S. This makes things a lot easier to understand. Plugging in the integers is a good way to find out the scales, and yet there's also another way to find these out more directly when looking at the triangle. I stumbled across this when I was studying the major scale early into my microtonal education. If you look carefully at this triangle, you can see that all of these EDOs, or equal temperaments, are just combinations of 7 and 5 added in different ways, and then the triangle tells you how many of these 7s and 5s there are. Weird, huh? Expressing the equal tunings as additions of these integers is a process that I label the process of using determiners. These integers are called determiners. By the way, I lied about deviating into 3-scale territory. Let's go there for just a moment, because this is where the determiners might actually be a little bit useful. Determiners act like scalar class sets in that you can leave the L, M's, and S as variables and figure out the framework in which to change things. I'll circle the determiners in this next little demo. With two terms, your determiners are just the number of tones and the number of L. This is the case with 5L2S, where the determiners are 5, that's the number of large steps, and 7, the number of tones. And so the equal tunings are just various combinations of 5 and 7 added. When determiners are used with 3 step sizes or more, there is just a process of consecutive adding. For example, with 1L 5M 2S, I start with the number of L as my first determiner, then add 5, then add 2. So my determiners end up being 1, 6, and 8, meaning that all 1L 5M 2S capable equal tunings can be expressed as combinations of various 1s, 6s, and 8s added together. And the 1s, 6s, and 8s all have to be included in the adding. This works with any number of scale steps, and the determiners can also be multiplied by subtractions of consecutively descending LMS steps to see how they line up, but we're not going to go over that. Anyway, back to 2-step size scales. When adding the L and S together to come up with the equal tunings, we run into a variant of something called the Frobenius problem. Here is a picture of Frobenius. Frobenius' famous problem is about these integers. If you are adding up 2 integers in all of their combinations, there is a number which eventually, if you pass it, all of the numbers above it can be represented by adding those very same integers. Pretty cool, huh? I noticed it when I was making these triangles. Also, integers that all have a factor in common aren't considered here because they just create multiples of that factor, like 2L, 2S. But the Frobenius problem is different than working with LS for a few important reasons. In each scalar class set, there is an equal tuning, which, once passed, can represent all numbers above it at least once, and I'm going to call this the cutoff equal tuning. For 5L2S, this is 35 equal, and you can see it on the triangle here, that 36 equal and up can all create a 5L2S. For 3L2S, this is 15 equal. For 3L4S, this is 21 equal. And for 1L7S, this is, well, 8 equal. And that should be obvious because of the little 1 there. In other words, the cutoff equal tuning is the highest integer that is not found in the triangle. The reason the Frobenius problem is different is that the cutoff number, or the Frobenius number, doesn't have to have both integers in it. Here is the equation for the Frobenius number. If a1 and a2 are merely the two integers, or number of L and T. Using 5 and 7 are determiners for 5L2S. We see that the Frobenius number would be 23. This means that any number 24 and up can be expressed as an addition of 5s and or 7s. That or is important. We know that the cutoff equal tuning for 5L2S is 35 equal. We can see on the triangle that 25, 28, 30, and 35 are missing on the way to 36 equal, and that they could all be written as 7 times a number or 5 times a number because they are in the columns and rows on the triangle where 0 is. My equation for L and S is a little bit different. It is actually simpler because the cutoff equal tunings share factors with the total number of tones. Here it is. Number of tones times L times the cutoff number, which is 1 for this inquiry. Let's check the example triangles we had. Yep, looks like that checks out. Now, let me tell you what the C is. The C is a cutoff repetition. It tells you how many times the equal tuning from then on will repeat. The Frobenius-like problem we just discussed only deals with C equals 1, hypothetically, meaning past the cutoff equal temperament for C equals 1, every equal temperament will show up at least once. Past a cutoff ET for C equals 2, every ET will show up at least twice. C equals 3 at least thrice, and so on. See, let's look at 1L7S to demonstrate. One more thing about the triangle. It lets us see the ratio of the large to small step, which Easley Blackwood calls R for ratio. These are not the same as frequency ratios, which other people discuss a lot more than I do. In 5L2S, the R approaches infinity as it travels along this line, and it approaches 1 as it travels along this line. This also means that in 5L2S, this line approaches 5 equal tuning as the small step gets closer and closer to 0, and that this other line approaches 7 equal tuning as the large and small step get closer to the same size. And this makes sense because of the empty numbers we filled in earlier. This is a well-documented case, 5L2S that is, and it works in the same way for every LS triangle. In the future, hopefully we'll talk about triangles like this with 3 or more steps and or the number of ways a scale can change or approach certain values. Thanks for watching. Please subscribe.